Hello everyone, my name is Cihangir Tezcan. I'm an assistant professor at Department of Cybersecurity at Informatics Institute of Middle East Technical University. This will be our first lecture for the course CSEC 513 Lightweight Cryptography for the Internet of Things. So in this first lecture I want to give you a brief introduction to lightweight cryptography and the IoT. So actually, I would like to define what IoT is, but unfortunately, there is not a proper definition for it because there is not an agreed upon definition for IoT. So for this reason, I would prefer to focus on NIST special publication 800-183, the title Network of Things, and this picture is actually taken from there because I found the definitions in this documentation really useful. So actually they first make this distinction. The term IoT, Internet of Things, actually is not correct because most of the IoT devices in the field are not connected to the internet, but they are connected to an internal network. So network of things actually would be a better term, but IoT is more widely used. So throughout the course we will say IoT, but most of the time we will be referring to network of things anyway. So this special publication actually gives us this big picture. So we have sensors and they are gathered together in clusters, and we have many clusters, and these sensors gather some data and constantly send it to the aggregator. So we have some aggregators here, and depending on the data we gathered, these aggregators can perform some operations on the data or send it to a computer or a server, and the server might do some computations and tell the aggregator to send some data to sensors so that they act in a different way, and so on and so forth. So this is roughly the picture about what IoT is for us. But of course, this is not the whole picture. There are many different networks, but even in this picture we can see what can go wrong. For instance, sensor networks. In the area of sensor networks, actually these questions are already discussed. So can we put can an adversary put a malicious sensor here and send false data to the aggregator? So there's an authentication problem here. Moreover, is the communication between the sensors and the aggregator are secure? In other words, is there a proper encryption here? So actually this course will be about this most of the time. So as you can guess, there many things can go wrong, and unfortunately many IoT devices don't come with encryption, or they use some algorithms which are not good enough, or which are not good compared to modern cryptographic algorithms. So let's keep this picture in mind, and I would suggest you to read this special publication, A Network of Things, to get a better idea about things. So even by keeping this picture in mind, let's talk about why we need lightweight cryptography. So main reason we need it for the encrypted communication. So we need it for security. As I told you before, we want this communication between all of these devices to be encrypted. Otherwise, we cannot talk about security here. But you might ask why the word lightweight and not cryptography? Because these sensors most of the time don't have good computational power, but actually this depends on the setting. For instance, if you are using devices like Raspberry Pi here, they are no different than a desktop computer, so you can do almost anything with those devices. But sometimes you have sensors which have very limited computational power, very limited battery, and so on. So we have some kind of different algorithms that we call lightweight cryptographic algorithms, so that it will work properly on these sensors. So mainly we need it for encrypted communication, but we also need it for authentication. So we need actually an authenticated encryption, and in our last slides I will talk about the standardization process of NIST, which is about actually a competition about authenticated encryption algorithms. And we also need lightweight cryptography for the battery life, because these devices most of the time run on batteries. So if your algorithm, your cryptographic encryption algorithm is demanding, then your battery of devices would not last long. So you need an algorithm so that your devices can have a longer battery life. We also need lightweight cryptography for energy, because most of these devices don't have much computational power, and they run on batteries, so some algorithms might not be suitable for these sensors. Another problem, actually another reason we need lightweight cryptography is latency, because in some IoT networks some sensors are constantly sending data, and receiving the data in a short time or in a timely manner is important in those networks. So latency becomes a important point. So if your encryption algorithm is causing some huge latency, then this would be something you would not prefer. Another thing we need to consider is throughput. Throughput in a network of things actually depends on your setting and your transmission data and so on. We generally assume that we don't need to send too much data or large data in IoT settings, but it depends on the application. Sometimes maybe you need to send a lot of data in a very short time, so throughput might become important. For at the desktop or server level, this is not a problem, because our current CPUs and GPUs are really fast. In a recent work, we actually achieved hundreds of gigabytes of encryption per second via GPUs. But for this kind of small devices, your lightweight cryptography algorithm should be good enough so that it provides proper throughput. Again, it depends on the application. Last but not least, we need lightweight cryptography because we need side channel resistance. This is very important, and this is actually maybe the most important thing for the IoT devices, because in general setting for the encryption devices and so on, our cryptanalysis effort only focus on the algorithm. We assume that the attacker doesn't have much control over the device. But when we are working with small devices, like the devices that we use in IoT, attackers sometimes may get physical access to the device. So for instance, the adversary can measure the power the device is consuming at the time and so on. And just by looking at these physical properties, the attacker might capture the secret key and break the system. So in those cases, the algorithm might be secure, but the attacker is actually attacking the implementation. So this is what a side channel attack is. And sometimes you might not even need to physically be near the device, but for instance, in cache timing attacks, all you need to have the access to the cache timing or the timing of the process. So this is very important, and we will talk a lot about this. But once again, here it doesn't matter if your algorithm is secure in terms of cryptanalysis, because you're not breaking the algorithm itself, but we will be going to breaking the implementation. So it is really important. So let's look at the big picture. Cryptography actually solves a lot of problems. like confidentiality, we provide it by block ciphers or stream ciphers or public key encryption algorithms like RSA, or we have authenticated encryption algorithms. But other problems we solve are like data authentication or integrity, which can be provided by hash functions, message authentication codes, and again authenticated encryption algorithms. And we also solve the problems of entity authentication and origin non-repudiation, which can be solved by digital signatures and so on. So we have a lot of cryptographic algorithms, as you can see in this picture, but we also need the lightweight versions of these algorithms. So in this lecture, we mostly be focusing on block ciphers, stream ciphers, authenticated encryption algorithms, and MAC algorithms or hash functions, but at the lightweight level. So let's start by giving a brief introduction to cryptography. This wouldn't be a proper classification, but maybe we can classify cryptographic algorithms as keyless algorithms and keyed algorithms. Cryptographic hash functions or similar algorithms do not use a key, but we have keyed algorithms that we call symmetric key and asymmetric key cryptography. And for the secret key algorithms or symmetric key algorithms, secret key algorithms use the same key material for both encryption and decryption, hence the name symmetric key cryptography. There are three types of algorithms in this category: block ciphers, stream ciphers, and message authentication codes. And if you have taken a crypto course before, you have seen examples of these algorithms, but in this lecture, in this course, we will be focusing on the lightweight block ciphers, lightweight stream ciphers, and lightweight message authentication codes. So these we classify them as we did here, but sometimes one can be obtained from the other and so on. And I summarized it here. Block and stream ciphers are encryption primitives, while the message authentication code is used for data and data origin authentication. We can use a block cipher to build both a stream cipher and the message authentication code. We can even use it to make it a keyless hash function. So although these are different subjects, we can obtain one from the other and so. Asymmetric crypto systems are somewhat different. They have different types of algorithms like key agreements, encryption, and digital signature algorithms and so on. But most of the time they are more computationally demanding algorithms. This is why for the lightweight crypto course we will be focusing mostly on the symmetric crypto systems. So let's define what a crypto system or a cipher is. So first definition we need to give is for plain text. Plain text is what you want to protect. So this is the data you want to protect. And a crypto system or a cipher is just a pair of algorithms that convert plain text to ciphertext, like here, and convert ciphertext back to the plain text. So it is just a pair of encryption and decryption algorithms. And the ciphertext is the encrypted version of the plain text, and ciphertext should appear like a random sequence. So we assume that all of our communications are performed in an insecure channel, and in real world this is the case. If you are using wireless communications like Wi-Fi or GSM communication, or even if you are using a wired communication, an adversary can get through and listen to the data you are sending. So we are always assuming that the adversary has the ciphertext. So, but it should look random. So by looking at the ciphertext, the adversary would not be able to go back to the plain text without the knowledge of the key. So we define the symmetric crypto systems as follows. For these algorithms, we have some secret information that we call the secret key, and this secret key is used for encryption and decryption. So communicating parties should have the secret information. Let's look at what a block cipher is. Block ciphers operate on b-bit blocks of data. So the plain text is divided into b-bit blocks. Each block is encrypted by a secret key K to produce B-bit output, and output blocks form the cipher text. Of course, how we do it depends on the mode of operation, so we will in the future see how we can use the block cipher algorithm. But mainly a block cipher and the chosen key is actually a permutation from 2 to the B elements to the 2 to the B elements. And for this picture, most of the time we choose block size as 64 bits or 128 bits, but some lightweight crypto algorithms even choose the block size as 32 bits. For the key size, modern cryptographic algorithms, for instance AES, can have key sizes like 128 or 192 or 256 bits. So in lightweight crypto algorithms, most of the algorithms use this key length, but we have many designs that are using less, the key size of like 80 bits or even less. So I will mention this in a few slides later, but using any algorithm who has shorter key than 128 bits actually makes no sense in today's world. So we strongly recommend that people are using at least 128-bit keys or symmetric key encryption. I will explain why this is important. So maybe probably the best known block cipher is DES, Data Encryption Standard. It was designed by IBM in 1970s and it was based on an earlier design by Feisal. In 1976, NSA tweaked the algorithm by changing its S boxes. So actually this modification made the algorithm stronger because NSA knew the technique of a cryptanalysis technique that today we call differential cryptanalysis, and they changed these S boxes so that they become a stronger encryption algorithm. But their modification also reduced the key length, which made this unusable after 1990s. So this algorithm has a block size of 64 bits, key length is 56 bits, and it has 16 rounds. Currently this is known as data encryption algorithm because using the word standard is misleading and people are still using this thinking that it is secure. So changing the name is a good idea. It became useless after 1990s since its short key is susceptible to brute force attacks. But as I told you, people are still using it and we are still seeing some applications for mobile phones are still using this as if it is a secure algorithm. This is replaced by AES, which is short for Advanced Encryption Standard. It was designed by John Damon and Vincent Raymond. It was standardized in 2001 by NIST. It was the winner of the AES competition, so the original name Rindell, the algorithm name Rindell, became AES. There were other finalists like Serpent, Twofish, RC6, and Mars. AES has the block size of 128 bits. It supports these 3 key lengths, and depending on the key length, the number of rounds becomes larger. And as far as we know, this algorithm is secure against known attacks. So known attacks are ineffective, so we can use it in our daily lives. And most probably most of the encryption in today's world and on the internet is done by AES. So at this point, we have a secure algorithm, so why don't we use it for everything or every device or every system we have? Actually, this is the suggestion by NIST. NIST says that if you can use AES in a device, in a platform or in a system, then you should use AES. But if you cannot use it due to the reasons like your device doesn't have the capacity, like the computational power or the battery power and so on, then you might need a lightweight cryptography. So this is the approach of NIST. NIST suggests the use of AES and says that if you cannot use it, then you should go to a lightweight cryptography algorithm. So many modern cryptographic algorithms are designed for desktop computers or servers, so we don't have any problem on our computers. But they may not fit into many IoT devices, or when they did, their performance may not be as good as they expected. So remember the second slide of this lecture. I told you that also we use cryptographic algorithms for security. We also need them for battery life or latency and so on and so forth. So for the device, IoT device, using another algorithm, a lightweight algorithm than AES might be a better solution.